Hello YouTube. Hello YouTube. Now you've probably heard of this. You've probably heard of this thing called the law of non-contradiction. It's one of the three classic laws of thought, and this is the fairly intuitive idea that it's not possible for two contradictory statements to both be true, or both be false for that matter. So formally, not A and not A. This has been the orthodoxy for thousands of years. In the history of ideas, at least in the Western world, pretty much everybody has taken this law to be self-evident. Actually, there are other traditions, Eastern traditions, where this isn't really so obvious, but certainly within Western philosophy, historically, nobody really questions this. In fact, very few people have bothered defending it because it doesn't seem to even need a defence. It's just that obvious. So I want to give a brief introduction to Dialetheism, which is the view that there are true contradictions. Or to put it more formally, it's the view that there is at least one proposition of the form A and not A. Obviously, Dialetheism denies the law of non-contradiction. Now, I'm guessing that to most of you this idea probably seems fairly absurd, and indeed that is how it's seen by most philosophers. But one man in particular has pretty much built his entire philosophical career out of defending Dialetheism, and it's Graham Priest. His book, In Contradiction, is the Dialetheist Manifesto, and another book by him, Doubt Truth to be a Liar, expands quite substantially on many of the arguments. He's done a few other books, he's written a whole bunch of articles. Most of them are devoted to defending this idea that there are true contradictions. So we will be examining his arguments in some detail in this series. Now, I must say, before we sort of get started, Dialetheism is a minority position within philosophy of logic, and I mean philosophy of logic in general can seem quite esoteric, quite technical, quite divorced from other areas of philosophy. But non-contradiction, it's such a fundamental principle of reasoning that denying it touches on a whole host of different topics. So you really do engage with a whole bunch of different philosophical areas when you explore this idea. And just in general, I think it's a good idea to challenge every assumption, no matter how deeply held it might be. So I'm hoping that this series will make Dialetheism accessible to most of you. Right, first of all, I need to give just a little bit of background to set the scene. And the first bit of that is I need to talk just a little bit about logic. Nothing too difficult, nothing too formal. I'm going to try to keep this accessible, but I just need to mention a brief bit of history. Right, so among people who are unfamiliar with logic, and in fact even among people who've done an introductory course on logic, there's an impression that logic is a static, unchangeable thing. There's this impression that you have the rules of logic, rules with which you can assess the validity of arguments, and that's that. So for example, you have modus ponens. If A then B, A therefore B. And the idea is you can substitute A and B with any proposition, and the argument will always work. If these premises are true, then the conclusion will always be true, because this argument is a valid form. So an example of that argument is, if Frank Zappa is a man, then Frank Zappa is mortal. Frank Zappa is a man, therefore Frank Zappa is mortal. Pretty simple stuff. And then you have logical fallacies as well. So a logical fallacy that's related to this form of argument is denying the antecedent. If A then B, not A, therefore not B. In this case, you can have true premises and a false conclusion. It might look like a reasonable argument, but it's actually not. It doesn't work because the premises can be true and the conclusion can be false. So, for example, if Frank Zappa is a man, then Frank Zappa is mortal. Frank Zappa is not a man, therefore Frank Zappa is not mortal. Again, maybe that looks reasonable, but Frank Zappa might be the name of my fish, in which case Frank Zappa would not be a man, but Frank Zappa would indeed be mortal. So the arguments of that form don't work. Arguments of this form do work. And these are the kind of things that you'll learn in an introductory course in basic logic. And when you deal with simple examples like this, you can be given the impression that logical rules are sort of fixed and unchangeable and universal. In fact, this impression is completely wrong. It's not at all the case. Logic is an extremely complex field, and the fact is that logic does change. There is not one logic. There are many different systems of logic. They're not all compatible, and the dominant system has altered over time. So I want to give a kind of classic example of how logic can change. Consider the following argument form. All A's are B's, therefore some B's are A's. So an instantiation of this form might be all cars are vehicles, therefore some vehicles are cars. We might say all televisions are machines, therefore some machines are televisions. All rats are animals, therefore some animals are rats. And so on and so on and so on. This seems to be perfectly reasonable argument form, and indeed in Aristotelian logic this form is considered valid. So Aristotelian logic considers this form to be valid. And Aristotelian logic reigned for quite some time. But there's a very serious issue with this argument, and it's known as the problem of empty terms. Okay? So consider the following case. All unicorns are animals, therefore some animals are unicorns. Now this argument seems to be rather problematic, certainly less clear than all cars are vehicles. It seems that in this case we have a true premise and a false conclusion, or at least you could make a very good argument that you do. And the problem arises because unicorn is an empty term. It doesn't refer to anything that really exists. Now, Aristotelian logic seems to assume that all of our terms do refer to existing things, but modern logic does not make that assumption. So in modern logic, this argument form would be declared invalid. Okay? Aristotelian logic says this form is valid, modern logic says it's invalid, and it's because there's different interpretations of this problem of empty terms. So there's a simple example of how logic can change. Now, around the end of the 19th and the start of the 20th century, logic became dominated by a family of systems that have come to be called classical logic, a term which I think perhaps makes its provenance sound rather more ancient than it actually is. I don't really need to go into the details here, but if you ever do an introductory course on logic, you will be taught something along classical logical lines. And many of the more advanced developments of logic in the 20th century, such as modal logic, have been extensions, or at least began as extensions, of classical logic. I think it's still basically the orthodoxy within philosophy. Now the fine details, as I mentioned, don't matter, but I just want to point out that if we're using classical logic, there's a fairly simple response to the idea of true contradictions. So on sort of classical logical terms, we can easily respond to this notion of true contradictions. And this response is called explosion, or to give it its rather more eloquent name, ex falso quod libet. And this is essentially a proof that from a contradiction anything follows. Okay? So, let's assume that we believe in a true contradiction. Let's say we believe that God exists and it is not the case that God exists. So God exists and God does not exist. A fairly radical solution to arguments concerning the divine, but there it is. So we assert that God exists and God does not exist. A and not A. Well, from this, a simple rule of logic allows us to derive A. It allows us to derive that God exists. Because if we have A and if we have some statement of the form A and B, you can easily derive from that both of those are true. So from A and not A, we can easily derive A. We can easily derive God exists. That obviously works, yes? Okay then. Another fairly simple rule of logic allows us to create a disjunction. So we can say God exists or the moon is made of cheese, right? This is perfectly reasonable and intuitive, because a disjunction of two statements, so a statement of the form A or B, well, that's true just as long as one of the disjuncts is true, right? They don't have to both be true, but just as long as one of them is true, then the statement A or B is true. So if I say the sky is blue or the moon is made of cheese, that's totally cool because the sky is blue. So from a true statement, you can create a disjunction. And since we have derived A, we can go to A or B. We've derived that God exists, so we can say God exists or the moon is made of cheese. Right, now, from our contradiction, we can also infer that it's not the case that God exists, because we have A and not A, so we can infer not A. Well, what does this do to our disjunction? We have God exists or the moon is made of cheese, but God does not exist. So, therefore, the moon is made of cheese. I think this is a perfectly intuitive argument. I mean, each of the steps there makes sense, and it's also easy to see how you can replace the moon is made of cheese with any statement you like. And all of this, you can basically sum it up as this, and just read this symbol here. Just read this as from A and not A, we can infer B. So we can infer B from A and not A. That's what that means, that symbol there. And that's the principle of explosion. So it seems that there really can't be true contradictions, because otherwise everything would be true. And that's why it's called explosion. From a contradiction, everything follows. Contradictions are explosive. So in classical logic, we seem to have a fairly easy response, a fairly simple response to anybody who asserts that contradictions can be true. Now, the thing is, as I mentioned before, there are many kinds of logics, and in fact, this kind of argument, this explosion, this wouldn't be permitted in all systems of logic. It certainly seems like a perfectly valid and intuitive argument, but the inferences involved are actually somewhat controversial, or at least some of the inferences are. Since the mid-20th century, there's been a development of a wide variety of logics known as Paraconsistent logics. And these logics have different rules to classical logic, and they're able to handle contradictions without contradictions entailing everything. So essentially, explosion fails. Okay, the argument we just presented is invalid in a paraconsistent logic. So how does this work? Well, here's our explosion argument. A paraconsistent logic, it might disallow this inference here, disjunction introduction. It might say, no, from some statement A, we can't infer A or B. That's not allowed. So from A, we actually can't infer A or B. It might disallow that. Or it might disallow this sort of final step here. This final step is called disjunctive syllogism. It might not be valid to infer the truth of one disjunct from the negation of the other. So from A or B and not A, it might be invalid to infer B. I'm going to do a more technical supplementary video in which I kind of explain how one of these logics works, but I think that that's probably what you kind of need to know for this series, really. So I'll do that supplementary video sometime, but I think you can see how that kind of works. If you disallow either of these inferences, then obviously you're not going to get to that conclusion. Of course, we now have to ask, well, what's the point? Why bother doing that? Why should we bother, trying to allow contradictions, trying to handle contradictions? Well, actually, there are purely practical reasons for developing paraconsistent logics. I'll just mention a couple. This doesn't, really matter for this series, but it's nice to sort of just know a couple. One avenue that I believe is being pursued is in computer science, where you may have a computer that contains corrupted information which may be inconsistent. You still need to be able to handle that corrupted data, that inconsistent data, and you need to be able to make inferences from it in various ways. And clearly this can only be handled properly by a paraconsistent logic. So there's the sort of computer science application. Another application may be in modelling how human reasoning works. Very often humans can reason from inconsistent premises. For example, one of the biggest questions in science for half a century has been how to unify the sort of Einsteinian physics and quantum physics, which are, if taken together, then in the current interpretations they'd be inconsistent. And yet we're clearly able to make very specific and powerful predictions from them. We're clearly able to use these theories together to understand the world better, despite the fact that together they're inconsistent. And I don't think it's at all controversial to say that humans can have inconsistent beliefs. Contra the principle of explosion, this doesn't mean they believe everything. The principle of explosion may be an intuitively valid argument, but it obviously isn't how human reasoning actually works. So there are just a couple of practical applications, and there are others. But there's just a couple. Now, maybe unsurprisingly, there are those people who have wondered, well, maybe it's not just sometimes useful to be able to tolerate contradictions. If it's possible to create a workable logic in which contradictions are tolerated, could it be that contradictions really exist? Could there be true contradictions in reality? So I want to present some of the reasons why people have answered yes to that particular question. Before we address that, there's just one more question. Well, if we ask whether true contradictions really exist, then we're immediately confronted with another question, which is, what are contradictions anyway? We have a formal definition of contradiction, and that's A and not A. But formal definitions aren't always connected with how terms are actually used by people. So consider, for example, conditionals. Conditionals are statements of the form if A then B, and in logic this is symbolised A arrow B. Now, so just for example, if it starts raining, then I will get wet. If it starts raining, then I will get wet. If Oswald didn't shoot Kennedy, somebody else did. All those kind of statements, conditional statements. Now, in classical logic, conditionals are considered to be false only if the antecedent is true and the consequent is false, A being the antecedent and B being the consequent. So, in classical logic, if A then B is false, only when A is true and B is false. In any other case, the conditional is true. But what this means is that the truth of if A then B depends entirely on the truth of its simple parts. And what that means basically is that conditionals such as, if the sky is blue, then Frank Zappa was a musician, or if the moon is made of cheese, then 2 + 2 = 4, those conditionals would be considered true. If the sky is blue, then Frank Zappa was a musician. Well, in that case, A, which is if the sky is blue, that's true, and B, which is Frank Zappa was a musician, that's also true. So we would say that the conditional if A then B as a whole is true. Similarly, for if the moon is made of cheese, 2 + 2 = 4, well, that part's false and the second part is true, so the conditional is considered to be true. That is the formal definition of conditionals. But naturally, there's there's quite a significant degree of controversy over just what relation this formal definition in classical logic has to do with how conditionals actually work in our everyday language. And other systems of logic interpret conditionals differently. That's just in classical logic. That's what classical logic says about the conditional. But there's a big debate over, how that relates to our everyday concept of conditional statements. So what about contradictions? I think all I'll do at this point is just point out that, yes, there are questions about how exactly to define a contradiction. And yes, there are some big controversies over just what it means to accept that a contradiction is true. But for now, I think we can kind of safely skip this question. The details of it will become clear as we work through the series. But I think in the case of contradictions, the formal definition of A and not A, I think that matches the intuitive concept pretty well, and it doesn't seem to result in any kind of weird paradoxes like the classical logic definition of conditionals does. So I think we can use this formal definition, and we'll explore the sort of details of it more in later videos. Well, that's it for this for these preliminary remarks. And we'll in the next few videos start looking at some of the arguments for dialetheism. Thanks for watching, and I'll see you in the next video.